Hello, we are Team 1. Today, we'll discuss the challenges encountered in the construction of the glass hull designed by Rafael Vignoli to showcase lightness and transparency and the structural solutions adopted to overcome these challenges. Constructing a building entirely clad in glass presented significant difficulties in resisting strong lateral forces, including wind force and earthquakes, while maintaining its original shape. To address these issues, we examined three major structures: the cable truss for the glass facade, the rib-like large roof structure, and the main columns. Here's a brief summary of our findings. The glass truss transfers horizontal forces through positive compression cables and negative compression cables connected to steel plates. These cables direct horizontal loads to the core building of the conference hall, the foundation, and the roof structure. In the roof structure, compressive forces from the arch-shaped beams and tensile forces from the connecting tables are transferred to the main columns. To prevent buckling due to horizontal forces, high-strength concrete was poured into the triangular frames from the 17th to the 14th section of the columns, which are under the highest risk of buckling. The horizontal forces are then transferred from the 14th to the 11th section, moving through the steel conference hall structure to the foundation. Additionally, we explain the design of large compression steel members and W bridges as supplementary support elements for horizontal forces in the short direction of the glass hull. This week, we'll discuss the process of constructing this enormous glass hull, focusing on temporary structures and components used to counteract horizontal forces before the hull was completed, as well as an overview on the entire construction process. Do you remember when we explained the construction process of the underground structures using the top-down method? During the top-down construction from the first basement level to the second basement level, the steel structure of the conference hall located in the glass hull was built. During the foundation work, at that time, foundation columns for the pre-constructed pillars were extended from the first basement level to the bottom foundation of the third basement level. The main columns were then built up from these foundation columns. With the conference hall and foundation columns in place, the full-scale construction of the glass hull began. Tower crane. A tower crane was installed on the steel structure of the conference hall, which serves as a core and the foundation for the glass hull. The tower crane was used for the installation of the main columns, the glass truss, the vent stage, and the roof structure. Vent. As the height of the glass hull increased, the risk of external horizontal forces, such as wind force and earthquakes, also increased. Before constructing the glass hull, it was necessary to implement measures to prevent these forces and create workspace for continuation of high-rise construction, which could not be handled by the tower crane alone. Therefore, the construction company adopted the vent and vent stage structures. Before the glass truss, columns, and conference hall steel structure were integrated into a completed structure capable of resisting horizontal forces, the vent structure served as a primary support point for all horizontal forces. Vent and main columns. The construction company prioritized the construction of the main columns. Using a hydraulic truck crane, the column frames were welded to the previously mentioned foundation columns, and internal concrete was poured simultaneously. The tower crane was used to build the vent stage and supports at the same pace to support the main columns. The main columns were constructed up to the 9th section, or 27.5 meters above ground, using the hydraulic truck crane, and vents were constructed up to 42 meters above ground using the tower crane. The task of hydraulic truck crane is now complete. Next, a stage was constructed on top of the assembled vents, and a traveler crane was installed to continue the construction of the columns. The tower crane lifted the traveler crane to the upper stage. Using the traveler crane, the column frames were welded and the internal concrete was poured using tremie pipes. Continuing the construction of the columns up to the 17th section in the same manner as up to the 9th section. Installation of the glass truss. With the vent structure and the stage for the frame construction in place to absorb horizontal forces, the installation of the external glass frame could commence. Since the vent structure was only erected up to 42 meters, the installation of the overall external frame and glass cable truss was conducted up to 25 meters. The assembly and welding of the steel frame were repeated, and the mullion installation was conducted from 0 meters to 20 meters in one go. As explained last week, horizontal forces are transferred from the steel frame to cable truss. And here is the construction process of the cable truss. The upper and lower cables are pre-tensioned using the tension jack of the triangular tension plate at the lower part. Once the cable tension reaches the specified value, the tension plate is fixed to the lower work plate. The cable is connected to the vertical members of the cable truss, which serves as a core using cable grips and saddles. During the introduction of pre-tension, the cable slides into position through the cable grips. At this point, the positive compression cable is positioned outside the core, and the negative compression cable grip is positioned inside the core. After introducing the pre-tension, the stoppers between the cable grips and saddles are removed to induce sliding, guiding the cable to the stable position. This cable truss not only supports the glass facade, but also helps prevent the roof structure supported by two main columns from toppling over.